So if you are really organized about your notes so far in the course, all of this would already be in your notebook. I'm not presenting any new material, just summarizing it. Okay. And I need to, yeah, I started my recording, so it's good. So I need to, of course, erase this before moving on. So this is a good time for me to just summarize what we have here. So we started this discussion about kinematic rates, which is relevant in the context of fluid flow scenarios or any kind of continuous deformation where there is a fluid-like behavior. So we talked about spatial and material time derivatives. You could have the same quantity expressed in either a spatial form or a material form. We discussed what is the spatial derivative, which is the derivative of the function at a constant location or position in space, or the material derivative, which is the derivative for a constant particle. We give the symbol dg over dt, d in uppercase, is equal to the sum of the local derivative plus the derivative with respect to space multiplied by the component of velocity. So this term here is usually referred to as the local rate of change. The local rate of change, which is like saying what is the rate of change at a given position, and then this term is called the advection, where this is the rate of change due to motion itself. And we saw very specific cases. What if your quantity is of interest in the velocity? Velocity of a particle is the rate of change of position for a constant particle. And our favorite example is that baseball, which is a rigid body. So it's easy to define what is a particle in the case of a rigid body. But in deformation situations, of course, you are not going to deal with rigid bodies. You're going to deal with the shape changing situation. So you have to always keep tagging or keep identifying what is your particle. Your particle may not have the same shape throughout. That's the whole point of studying deformation. So velocity is the first derivative with respect to time for a constant particle. Acceleration is the second derivative with respect to time for the same particle. Once you obtain these in the material frame, you can easily do push forward, which is transforming to the spatial using what is the name for this function? Phi of x comma t is what? I know you're mouthing the answer. You are saying something, right? Wasn't that the answer? So in the start of this chapter, we saw x equal to phi of x. We gave this a name. This is called deformation mapping. Deformation mapping. And then if you have time dependence included with this phi of x comma t, it's a very simple name we gave for this mapping called motion. I think this is the third time I'm making this inflection suggesting that, oh, what is such an obvious concept you guys missed, and still you keep missing. Anyway. So we have motion, which represents the time dependence of the change in position in space versus the change in position of the particle. So if you use that, you can transform between the material and the spatial, or the spatial and the material. Okay, so this is a summary of section 3.6.1, which is spatial derivatives or spatial and material derivatives. There is still just one more concept I need to add here. I have some space here. While we calculate this quantity, we have, if suppose g is velocity of x comma t, you get the quantity partial derivative of velocity with respect to space dot or multiplied by vj, which you can write partial derivative of v with respect to or with respect to x. Yeah, with respect to x dot v. So this quantity here, if you write V is in general VI EI, this quantity partial V over partial X would be partial VI over partial XJ EI EJ, and this is given a special name LIJ called velocity gradient. Velocity gradient. This is one of the other important tensors. We'll write L tensor is equal to gradient of V. Remember, this is a spatial second order tensor. So that concludes 3.6.1. Okay. Any questions before we move on to the next section? So you can almost count that you have like 4 important subsections in this whole unit. So you're going to get a problem each from each of those subsections. You can almost say that now, and at the end of the lecture today, we'll have the mock exam. Like I'll give you 4 problems and ask you to try it. Okay. All right. There are no questions. I'm going to move on to 3.6.2. So 3.6.2 is the discussion of rate of change of local measures. Rate of change of local measures of deformation. So we started with ds, length, the rate of change of length. I'm not going to go through the whole derivation again, but we wrote that this is equal to Fij dot, the component of the deformation tensor, multiplied by dxj. Sorry. So when we talk about ds dot, we talk about length, but to introduce the concept, we wrote that ds is equal to dxi square root. So we are more interested in what is dxi dot, which is Fij dot dxj, and we found out that Fij dot is Lij times Fjj. Or you can write the deformation tensor, the rate of change of deformation tensor is the velocity gradient tensor dot f. If I ask you the quick question without showing you this part, what is the order of this quantity where L is a second order spatial tensor and F is a second order mixed tensor? What is your quick response? What is the order of this quantity? 2, 3, 4. These are your choices. 2. We went through this discussion towards the end of last lecture. You recall? Do you recall? Yes, no? So L is Lij, EI, EJ. F is, you can write F, K, K, EK, EK. Is everybody are we all on the same page about this notation? Second order spatial tensor, second order mixed tensor. Okay. So we are saying what is L dot F? That is like writing Lij, EI, EJ dot FKK, EK, EK material. So just don't change the sequence. This is a scalar, you can bring it forward. So Lij, Fkk, Ei, Ei, Ej dot Ek, which is delta Jk, Ek. So the new diode is EIEK. So this is Lij, Fjk, Ei, Ek, or if I don't like K, I'll call it Fj, Fj. So this is again a second order mixed tensor. So I won't ask the question in the exam saying here is L dot F, tell me the order of this quantity. That question that we are past that point. That was exam 1. In this exam, you will be asked to maybe derive or show something is equal to something which may involve these dot products. Okay. So this introduces a new quantity F dot, which is the rate of deformation tensor, and it's related to the velocity gradient and our original friend deformation tensor. So coming back to here, the rate of change of a length element dxi dot is Fij dot dxj, which is Lij F. What should I write? Lij Fjj dxj. What is Fjj times dxj? There is a repeating index in J material or uppercase J. So what is this quantity? Dxi lower cap. That's what you mean, Nikesh. So this is Lij times dxj spatial. What is the order of this quantity? How many non-repeating indices does it have? 1. So this is a vector or component of a vector which is a spatial vector, which is what your dxi dot is. So you have a I here, you have a I here. These are all sanity checks, consistency checks that your derivations must pass. So if you derive something or write an expression, I will be looking out for these. Okay, they have 3 or 2 indices in this row. Does it pass the consistency check? So you have to be careful with your use of indices and letters. That's the point I'm trying to make here. Okay. So anyway, step 1, rate of change of a differential length element. We just derived that result, which is dxi dot is Lij times dxg. And all this discussion is summarized in page 96, 97. 96, 96 actually, page 96. Any questions on this? The other purpose of me doing this summary today is in the textbook, I didn't cover everything. I skipped a few because I thought they are more advanced. So if you have a list of what we actually did and what will be on the exam on Tuesday, I think it will be easier to study. Okay. All right. So this is rate of change of a differential length element. Then the next quantity is rate of deformation and spin tensors. Actually, I noted this problem before. The book calls this rate of deformation tensor as D, whereas I call it F dot. I think it's a very confusing way to do that, but if it helps, you can just refer to this as F dot and F, and we'll reserve the name deformation for D. That's what the book does. So rate of deformation tensor, rate of deformation tensor D is defined as L plus L transpose divided by 2. And then rate of spin tensor is W defined as L minus L transpose divided by 2. So obviously D is symmetric and W is antisymmetric. So this is symmetric. This is antisymmetric. And we previously talked about the rate of change of a length element, which is along any one direction, dxi or dx1, dx3, and so on. If you think of what is the rate of change of length squared, where the length can be arbitrary, this is equal to dij dxi dxj. We did this derivation and I won't go through it again. But quick question, if you don't look at the left side, just looking at the right side, what is the order of this quantity? 0. It has no non-repeating indices. Both the indices will be summed over, so you'll be left with a scalar. Okay. You're taking pictures. I'll wait for 1 second. Okay, can we? And then under this heading, rate of change of local measures, we saw this like A, B, C, these 3 measures. And then the last measure we saw, that is the last lecture, we also saw rate of change of volume. You can also call it volumetric strain rate, like basically rate of change of volume. So we saw that this is equal to, so firstly you need to recall what is J. Anyone? J is the determinant of F, that's how you calculate it. Physically, J is the quantity that relates the volume change in the spatial frame to the volume change in the material frame. If your material is incompressible, that is, you have, let's say, water, even if you apply a lot of tension or compression on a liquid like water, you're not going to get a much appreciable change in volume. Usually, water's density can be changed by heating it, but it's almost impossible for you to compress water with whatever strength that you can get. It requires Herculean or astronomical strength to compress water, right? This is the basics of hydraulics. How does a hydraulic brake work? You have an incompressible fluid transmitting the force from one end to the other. So for such an incompressible material, no matter how much loading that you do, the change in volume, there is no change in volume. Your volume that is in the initial frame of reference is going to also carry over in this in the spatial description. So in this case, J is 1. If J is greater than 1 or less than 1, how will you interpret this? If you say that J is greater than 1, is that expansion or contraction? Expansion, right? J is greater than 1 means expansion, and then the other way is contraction. And since we are dealing with volume occupied by a bunch of atoms, there is no way in hell J can be less than 0. That's not possible. These are some basic facts about J, right? So we are now interested to calculate J dot, which we went through the derivation, is J multiplied by F inverse transpose dot double dot L. Is that correct? Yep. J inverse transpose double dot F dot, which is J times I, the identity tensor, double inner product L, which we showed is equal to J times the divergence of velocity. So the rate of change of volume is the value of the determinant multiplied by the divergence of velocity. You may recall from fluid mechanics or from solid mechanics, whenever you hear the word incompressible, you first write del dot V equal to 0. And we'll use this result in the next unit to derive the equations of mass, momentum, and energy conservation, especially mass conservation. Okay, so this is a result which we will use. So this is D, the rate of change of volume. There are a few more subsections under 3.6, which 3.6.2, which I didn't cover. But if we get a good idea of A, B, C, and D, I think we would have the basics, and then if needed, you can study that in the future. That's up to you. So this is where we stopped towards the end of last lecture. So questions or yeah.
J equal to 0, what does that basically mean?
So J equal to 0 is also not possible. I should include that inequality here. You can't make something to have a volume to go from there to not having a volume at all. At least within the framework of continuum mechanics, we are not in the business of making atoms or converting atoms into energy like nuclear physics. We have a bunch of atoms, we call that a particle, we look at the deformation or shape changes to that particle. And at all points, I said this at the start of this class, at all points there are enough atoms in our particle to call it a particle. If you are dealing with 4 atoms, that's no longer a particle. So J equal to 0 is not a possibility that we have in our thinking. Any other question? Take a picture. All right. Then this wraps up 3.6.2. And now that brings me to the very last topic in this unit, which we are going to discuss for the first time. Three point 6.3, Reynolds transport theorem. So until so far, we have discussed the rate of change of quantities, which are all differential in nature. So what are differential quantities? We have dx or dx. So how do you define this dx? Suppose you have a point that has a position x, and then you have a neighborhood point, we'll call it p dash, which has x plus dx. So you can draw a vector, this is x, and then they say this is dx. So you can look at it both ways. You can say this unknown vector, which we will call as x prime. If you just did basic vector algebra, this is x plus dx. O to p and then p to p dash is equal to O to p dash is equal to O to p plus p to p dash. Right? So we dealt with dx or dx, or we dealt with the components. Okay. We talked about length, ds squared, which is dxi, or ds squared, which is dxi. This is length squared, magnitude squared. And magnitude itself is ds equal to square root of dxi, or ds equal to square root of dxi. These are all measures of length. Okay. We also talked about area. So we can think of n cap dA or n cap dA naught. So if you have, we call this your area of interest. Every area is defined by two attributes. What are those attributes? We would have seen this in your geometry or calculus courses. What two things when combined form an area vector?
Length and
No, sorry. The area has two things. If you want to call something a vector, it has to have two things. What are those?
close shape.
No, we are not talking about closed or open areas. So a vector has a direction and a magnitude. So if I write S is a vector, what I mean is S as a magnitude and S as a direction. When we talk about an area, the way we define area vectors is you have an area which has a magnitude, so the area of the shaded zone multiplied by the normal vector perpendicular to the area. So we always define the area through its normal vector. So when we write n cap dA, we assume this area is dA and n cap is the vector that is perpendicular to dA. So we write dA vector is n cap dA. Or you can write dA naught is n cap dA naught in the material frame of reference. This is a differential area element, just like this is a differential length element. What is the magnitude of this area? Right here. What is the direction? Right here. So we saw how to relate the change in length or position vector. We saw how to relate the change in area or area vector. And we saw all these through the deformation mapping. So what is the relation between dx and dx? This is, by this time we have seen this so many times. What is dx? F dot. Should not say into. You say dot. You're going to complete this course. Dx is f dot dx. This is the definition of what is deformation mapping. If you know the deformation mapping, you can compute everything else. That's what this whole section is about. And we also saw section 3.4, which we are going to recap also today. So this is, if you know this, you can get all these quantities. With me? And how do you relate n cap dA with n cap dA naught? You may not remember this directly, or maybe you do, but if you look at page 81, section 3.4, page 81, section 3.4.3, n cap dA is equal to J times F inverse transpose, J times F inverse transpose dot n cap dA material, and this is equation 3.9. So this is differential length element, differential area element, and then we can also think of volume. You have dV and dV naught. What is the relation between them? dV is equal to J times dV naught. Again, I might have said this a couple of times before or more. If you know deformation mapping, you can predict length changes both ways. If you know this, you can calculate this and vice versa. If you know the deformation mapping, you can calculate area changes both ways. If you know, if you know F, you know F inverse transpose, you know J, you can get this. Again, if you know the deformation mapping, you can get J, which will allow you to calculate differential volume changes. Are we together so far that we can handle differentials? What is differential? Small change in length or small change in area or small change in volume. We can handle all that back and forth. That alone is not sufficient to describe real world engineering applications. Why? You tell me. Knowing this alone is not enough for you to analyze any engineering problem. Why? You tell me. The complexity of shape. Not only that, the finiteness of everyday engineering objects, or not even engineering. Real objects have everything finite. They have a finite length, area, or volume. Mathematically, these are differentials. If you want to get the total volume or total area of a surface, and you know a differential value, how would you go from differential to the total? So if I want to know, I have let's say a component that is oriented along the x-axis or axis 1, and it's between x1 equal to 0, x1 equal to L. What is it's a trivial question to ask. What is the length of this object? L. And that length is not something you would just say L because it happens to be between 0 to 1. Mathematically, L is 0 to L dx1. Or if I want to know, let's say I have a sphere that is at the center, and I know the equation of the sphere is x1 squared plus x2 squared plus x3 squared equal to 1, let's say, or r squared, something. What is the volume of the sphere in mathematical terms? The volume of the sphere is V, is triple integral of the function that describes the shape, which can be a sphere or which can be something else, integrated over the spatial extent of that shape. That's the mathematical way of saying what is volume, right? So your complex object could be an axle or a bone or something. If you can describe its shape in terms of geometry, like an equation that describes it as a cone or a sphere or an ellipsoid or whatever, or if you have a bunch of data points that you may extract, how do you tell us how do you extract the shape of a bone? Suppose the bone is something not from a living subject. You have recovered the bone and it's in your hand. How would you know the shape, or how would you get the shape of that bone to compute its volume?
Pictures.
You can take pictures in various angles and try to create a three-dimensional representation. You could do a CT scan. You could get a representation, and then you can get a CT scan at various angles and get a 3D representation of the bone. What is the 3D representation in the computer? A digital representation is nothing but a bunch of points. Each point has XYZ coordinate. Right? You would scan an object. It need not be just a bone. It can be a machine component or structural component or whatever. Doesn't your department have a CT scanner? Oh, you're not from civil engineering? Ah, okay. I've been thinking you are a civil engineer.
It's close, but
Not really close. Okay, good. Okay. So anyway, you can take an object and you can get a 3D representation of it, and it involves a bunch of XYZ points. Your points may be part of a function. If you know the function, the integration is easier. But even if you don't know the function, there are numerical integration techniques from which you can calculate volume. So if you can put yourself into a scanner, like a full whole body scanner, you can get a mapping of your entire shape, and from that you can literally calculate your own volume. It's possible, right? So the point I'm trying to make here is, if you have these relations which describe the change in value for differential quantities, that alone is not sufficient for us to do engineering problems. We need a method that will allow us to work with finite or integral quantities. That is what we are going to see in terms of Reynolds transport theorem. If you go to the book, I'm going to read a sentence from the book. So far, this is 3.6.3 Reynolds transport theorem. So far, we have discussed the time rate of change of continuum fields. Now we consider the rate of change of integral quantities. That's it. They don't give you all this backstory about why we need this. I'm giving you that because if you just have these, it won't help you solve the problems that you care about. It will just be remain as mathematics. Okay? And you guys should have really taken this course with Dr. Tadmore, who is an engineer, but he's also a mathematician. In his class, he'll be like, this is obvious, this is this. I struggled so much. I think I got a B minus or maybe a C plus. I really struggled this class. But anyway, that was 15 years ago. Of course, you are going to get better grades than me. All right, so if I have a quantity G of x comma t, I can integrate this quantity over a finite volume. And to denote it's a finite volume, I'm going to write a triple integral. I'm going to get a quantity which I'll call I. G is the quantity per unit volume, and I is the total amount of quantity. To give you an example, consider G of x comma t is density of x comma t, which is mass per unit volume. So if I do density integrated over a finite volume, that will get me M, which is the total mass contained in the volume. So the convention we are adopting is we will use lowercase letters to denote any quantity that is per volume, and then an uppercase notation to denote any quantity that is a total. Okay. This total quantity I always scales with volume. Would you agree? The more volume you have, the more stuff you have. So if you think of the density of air, it's about 1.1 kilograms per meter cube. If I ask you what is the total volume of air contained in this whole building, what will you do? You'll take the density, multiply by the volume of the building, which is a catch because the building is not just space, it is also these structures. So you will have to take the whole volume, but take out the structure, which is the volume occupied by the pillars, the roof, the floors and everything. And then you have to get me a effective volume of the building, which is total minus the structural volume. And then you have to take that volume, multiply it by the density to get the total volume of air in this space, right? So first thing we want to introduce is integral quantity I is the integral of something per volume multiplied by the total volume. Okay, with me so far? I'm going to introduce another quantity here. Suppose if you have a velocity v, okay, I let's say I have like a balloon, okay, like a container or something that looks like a balloon, and I have a hole which is oriented at a certain angle, certain direction. Now, because I fill this balloon with water and I'm deforming the balloon or applying a load from the below, basically squeezing it from the below so that the water jets out. Okay, and it jets out with the velocity v. Okay, so how will I get the flow rate of, in this case, fluid or whatever you want to call it, v? So the flow rate is v dot n cap dA. Why do I write that? Because the velocity could be in any direction. Suppose it's jetting out in this direction. The normal component or the component that is along the normal is the only one that contributes to flow. The component that is perpendicular to here means it's not contributing to the flow rate. Why? Because if you are metering, how will you actually know the flow rate? You will put a device or some kind of a sensing, and whatever reaches this section is what you will call as the flow rate. If it doesn't reach this section, it's not part of your measurement or counting procedure. So this V dot N dA integrated over the cross section area, which is the total area, would be my flow rate of fluid across A, or across area A, which is n cap A. When you are analyzing components or loading or deformation or materials, there are only two types of measurement or two types of analysis that you can do. Either you can measure something that depends on the volume, like total amount of material or stuff, or some kind of quantity, or you have stuff that is coming through a surface or across a surface. Let me give you an example. How do you measure mass? You put it on a weighing scale. The weighing scale detects the gravity force which is exerted by the entire body. So it is a measurement that is proportional to the volume. Of course, density is involved. That's a material property. But the more volume you put, the more mass you're going to register. Another example. How do you measure heat flux? Heat flux. If you have a burner, okay, you put your finger on it. Of course, it's hot. How do you measure how much power or thermal energy is coming out of the burner in that area? You put what is called as a heat flux sensor. You paste it at any spot. It will record the flux registered in that over that area. Your heater can be as big as you want. It can be as big as this room or anything. But what matters is wherever you paste the sensor, it can only detect what happens in that surface. That's an example of a surface measurement. Same thing goes with this example. The rest of the size or shape of this whole structure doesn't matter. What matters is the flux that is coming across the surface, and surface is defined by its area. So when we are making any measurements, we deal with two kinds of quantities: volumetric rate of change and surface rate of change, or which we call flux. And we need a practical relation that connects between these two, because sometimes one is more convenient than the other, or to measure or to calculate. So we need a relation between these two, and that's what Reynolds transport theorem provides. It provides a relation between the volumetric rate of change and the surface rate of change. So this conceptual kind of background will hopefully allow you to then start with this equation I. I have an arbitrary volume. Okay, let's say I have an arbitrary volume, and I am writing. Forget the uniform sphere that I talked about. Let's say we consider some component or some volume of material. We write I is equal to integral of the quantity G, which is quantity per unit volume. Okay. We want to next ask the question, what is the rate of change of I dot? How to compute I dot? Eventually, we want a very simple relation for I dot in terms of the surface rate and volume rate. Okay. What is I dot? I dot is I dot is the rate of change with respect to time of this quantity G, which depends on space and time. And this is in the spatial frames. That's why I'm using lowercase x. So I have G as x and time, which I'm also allowed to write. This is d over dt integral. This is v G with a tilde of x, which depends on x and time, comma t, and then I'll write dv naught v naught. I have mapped or transformed a spatial representation into a material representation, nothing else. This is an example of a pullback operation. Okay. So here is a very subtle point. I want you to listen, not write. Take a break. Okay. When we write rate of change of volume. Okay. Now think of this object. Okay. Some kind of balloon or some shape that I'm squishing in my hand. What is the idea of a reference configuration and a spatial configuration? You tell me. We've been talking about this for many weeks now. What is this reference? What is this spatial?
Reference would be the particle that we're paying attention to.
So reference configuration is the one. Before you started the act of deformation, you would have a shape, right? Call that a reference. Of course, the shape is going to change, but once you have taken a picture of it and you are calling it a reference, then that with respect to that coordinate system, you can describe everything else. Or in other words, the reference configuration is a constant in time. It doesn't change because you took a photograph before you started your experiment. You call that as a reference, and then your deformation happened. So depending on at what time point you are in your deformation process, this volume changes with time. Do you agree with me? This is a function of time. At every instant, you can define a spatial coordinate system because your deformation keeps happening, your shape keeps changing. Okay, but this reference is not a function of time. Would you agree with me? Right? If it is not a function of time, I can first do the differentiation and then do the integration, or I can do it the other way. I can flip this order because this volume is a constant in space or constant in time, sorry. So I can write this is integral over V naught of dg over dt times dv naught. I didn't write it in words. When you go home, it might not sink in, but if you want to write down something, what I want you to write down is the reference configuration is chosen before the deformation starts and is a constant with respect to time. If you want, you can write that down. The reference configuration is constant in time because it's like defining something, calling it a reference. It doesn't have to be staying there. You have the memory of it to continue working. Okay.
It's spatial coordinate at t equal to 0.
It is, yeah, you can say it coincides with the spatial coordinate at t0, or at t0 reference and spatial are the same thing. At later times, spatial can be defined at every time point, but reference is one thing. That's why it is a reference. The word reference means there has to be only one thing. You can't have 5 things and call them reference. Oh, and so it should do this because I went from spatial to reference. This dv, this g becomes g tilde, this dv becomes j times dv naught. J times dv naught. J times dv naught. I should write d over dt of g tilde times j times dv naught. It's important because next step we have to split this or expand this. Okay. All right, some basic algebra. So derivative with respect to time of g tilde times j, which I write g tilde times j dot is g tilde dot times j plus g tilde times j dot. Chain rule, right? UV. Differentiation of product is just UdV plus VdV. All right. What do we know about J dot? We saw that in under this section 3.6.2, where J dot is J times divergence of V. So this would be G tilde dot J plus G tilde J times divergence of V. V is a spatial quantity. Remember, V is a spatial quantity, but we are invoking it because it will allow us to simplify everything. So this I'm going to write is J times G tilde dot plus G times divergence of V. So if I bring that result back here, so this result I dot or this quantity I dot is triple integral over V naught. I need to substitute for this. This is J times G tilde dot plus G tilde times divergence of V multiplied by dV naught. With me so far? So here's a trick. You have integral over V naught, and we are going to combine JV naught, J times dV naught, and we are going to actually go back to the spatial frame. So this quantity J times dV naught becomes dV, and what is G tilde dot? If you want to go that, go back into spatial. Is that correct? So if you have G, a quantity being represented as G tilde in the material frame, going to G in the spatial frame, literally how would you do the transformation? You did this example when you did acceleration and velocity, first calculate them in material frame, then put them in the spatial frame. What missing link would you put here? What is needed to go from here to here? If you know the motion, which is x equal to phi of x comma t, either the motion or its inverse. If you know this transformation, then you can transform from here to here, right? So this is always assumed to be known because that is what this whole unit is about. Here's a deformation, how to analyze it. If you ask the question, what caused the deformation that involves loading, the answer to that is in the next unit. Okay. So we have, when we go back to the spatial frame, we have V. First I will write dV. Then I have G dot plus G tilde becomes G, And what does del dot V become when you transform from reference to spatial? L, no, L is gradient, del gradient of V, not del dot. Question is, when I go from referential frame to the spatial frame, what happens to del dot V? Who had nothing as an answer? Nothing, it's already in the spatial frame. There's nothing you need to do or you can do. It just becomes del dot V or just stays del dot V. That's it. So whatever was previously in the spatial frame has now been transformed, sorry, in the reference frame, referential frame is now being transformed to the spatial frame. So this relation that you have I dot is equal to G dot plus G times divergence of V. This quantity, this relation is what we call the Reynolds transport theorem. That is, if you know the instantaneous rate of change at a given position, what is G dot? Recall that. What is G dot? G dot is partial G over partial T at a fixed position. What is divergence of V? That is partial Vi over Xi. And both these are functions of space. This is a scalar, this is a scalar. There is the sum of two scalars, which is a function of position xy, x1, x2, x3. And then you are integrating over the entire volume. So this quantity gets you the total rate of change of that quantity for a finite sized object. Okay. So this result, if you know the spatial representation, you can use it to calculate the total rate of change. This result is called the Reynolds transport theorem. Okay, it's a kind of a useful result to go from mathematics to actual engineering. And I'm sure Reynolds did well to discover this. Otherwise, why would they name it? So this result is useful nevertheless, but usually it is given one more simplification. We can write this result as triple integral over volume G dot dV plus triple integral over volume G divergence of V dV. So towards the end of the unit on tensors, we saw what is called as the divergence theorem, which equates this or converts this volume integral into a surface integral over the area G V dot N dA. How exactly you go from here to here, that's not important. I'll tell you what is important. You have a finite sized shape. The total rate of change of some kind of quantity, let that quantity be heat. The total rate of change is the sum of the heat production within the volume integrated over the entire volume plus the flux or the rate at which heat leaves the volume. And how can heat leave? Heat can leave only at interfaces where that object is in contact with the rest of the surroundings or atmosphere. And heat has to leave at a certain rate. It has to leave heat flux. This V is basically the rate at which the heat is transported. It could be heat flux, mass flux, or velocity flux. This V basically decides at what rate this is leaving. So it's a surface phenomenon. So the total change is the sum of the volume change plus the surface change. This is the interpretation which is more important. So if you know the rate at which a material is changing, the rate at which the material is getting transported, and what is V, the rate at which, I'm sorry, back up. The rate at which a quantity is changing, the rate at which a quantity is getting transported across an interface with a velocity V. If you know those three quantities, you can calculate the total rate of change using Reynolds transport theorem. So the most common classical way of representing this theorem is in terms of a volume integral plus a surface integral in terms of G V dot N dA. So this, what you may ask, what is V and what is A? You have an arbitrary shape. V is the volume and A is the surface. If you know this picture and this result, you should be able to solve engineering problems. Now you may ask me, where are the examples for those engineering problems? The hope is we teach you the concept and you would apply this for some problem that is of interest to you. Okay. So this wraps up our section 3.6. I'm at around 5:40. I can either go ahead and summarize the complete I'm going to summarize other three sections in this unit so that in one place we have all the entire summary, and then we'll take a break. Okay. So this is just the 3.6. Okay. Before I erase this, any questions, comments? We'll see if we can get an example in calculating this for a few G values. G functions. All right. So coming back to exam 2, which is due on, which is going to be on Tuesday. If I were you, what information or summary do I want to prepare for this exam? Firstly, what do you want to know? The format. What is going to be? How many questions are there? Will there be? So section 3.4. Okay. Oh, so exam 2. We are going to have again 4 problems. One of them will be a question like you had last time, but 3 like actual problems. Okay. And this one question will be from section 3.1, which is the discussion about what is a continuum party. And these 3 problems, of course, we had section 3.6, 3.4, and was it 3.2 or 3.3? Three point two and 3.3. So you'll get one problem each from these sections. Okay, and you can bring your notebook, textbook, but no internet. You can bring any other textbook if you want, or any written material, that's fine, but no devices. Everybody clear? You need a textbook if you want, if you plan to refer to your book often. Think about it. No devices, but you can bring any notes. You probably won't need a calculator, but you can keep one. I don't care, but don't use like a cell phone calculator. Bring a calculator frame. Any question about the format? Okay, same as last time except devices. Say something? No? Okay. All right. So section 3.1, 3.2 and 3.3 are pretty simple. So I won't summarize them again. 3.1 deals with continuum particle. 3.2 deals with I think spatial and material description. No. Deformation mapping. So 3.2 deals with deformation mapping, which you should be aware of by this point. Mapping x equal to phi of x. And 3.3 deals with spatial and material frames of reference. So you're going to get one problem from either of them, which I'm sure will be your easy problem. And then there is section 3.4 and 3.6. We talked about 3.4. I will say explicitly though we skipped 3.5. If you are not aware, or maybe you're wondering. 3.5 we didn't discuss it in class and I won't expect you to know it. Okay. What did we discuss under 3.4? This is description of local deformation. So of course we are going backwards. There we talk about rates. Here we talk about just the differential quantity, not of the rates. Okay. So we started with what is deformation tensor or deformation gradient. 3.4.1 deformation gradient. F tensor is the gradient of x with respect to material x, or written as x over x. I like doing this. Fij is partial xi over partial xj. Mixed order second order mixed tensor, and dxi is Fij dxj, or dx equal to f dot dx material. Okay, that is 3.4.1, introducing what is deformation tensor. Does anybody want to take a picture? Good. Of course, you get 80 minutes to do this. I didn't write it, but same as last time. So that was 3.4.1 deformation gradient, which is given as so then 3.4.2 volume change. So I'll also write key equations because will be helpful, I think. This is equation 3.4. This is equation 3.3. Volume changes. dV over dV naught equal to J. This is the equation 3.7. Is also equal to the determinant of F. And we also define what is called as the right Cauchy Green deformation tensor, which is given the symbol C, which is F transpose dot F. I'm not big on names, So if you don't remember that C is called right Cauchy-Green deformation tensor, I won't hold it against you. If you ask me, I also won't remember this. Okay, but what matters is a quantity which is the transpose of the deformation tensor dot the deformation tensor is important. If you should remember or at least know that. I don't care for the name. Okay. So C defined this way is a quadratic tensor. Is C a material or spatial tensor or a mixed tensor? It's a material tensor, and you are saying this because F ij is the spatial is the mixed tensor. So you write F is equal to Fij Ei Ej. If F is this, what is F transpose? We discussed this at length. Before you say, a transpose is a reversal of index or a reversal of the dyad. I'm asking. What is the difference between transpose and inverse? Sorry, yeah, transpose and inverse. So if this is F, can somebody tell me what is F transpose? F capital I. I think I'm sorry to say you're talking about inverse. It's a reversal of the dyad sequence, right? So this is again Fij, but this is Ej Ei. If F is given as this, see, there is a degree of arbitrariness to everything. Why Ij? Because I wrote it. If you wrote it, you would have written differently. So if this is the dyad sequence, what matters is the dyad sequence is reversed. So this is again Fij, but Ej Ei. I'll write reverse the dyad sequence. It's still a second order tensor, still a mixed tensor, but the dyad sequence has been reversed. So if you now take F transpose dot F, and if you are me, I'm in the exam, I'm very likely to do this. I would not remember that this is a material tensor. Of course, I would remember if I do 100 problems, but if I didn't do, I would at least remember this principle. What is F transpose? F ij ej ei. What is F dot? I'll have to use different letters. I'll use F jk ej ek material. So I have ei dot ej, which means I'll have a delta ij in the spatial. So that goes away. I'll have ej ek material, which will make this, like you said, a material tensor. So this would be Fij F I K E J E K. I is a repeating index. So I have, if I call this C, I can write this C I J or C J K E J E K, which will be equal to C. So it's a material tensor. I'm really hoping, even if you don't remember this fact, you would be able to derive this fact whenever you need it. Okay, so yeah, you can take a picture. I'm going to erase it, and we'll take our break after we finish the review. Okay. So a transpose is a reversal of the dyad sequence, whereas an inverse is something else. While we are here, let's also talk about if F is this. What is F inverse? F inverse is, this is what you try to say. This is F II inverse EI, or I'll say JI EJ. It's a reversal of index, so that if you have Fij multiplied by Fji inverse, you will get delta II, which is 1. Inverse literally means reciprocal. Okay. So inverse, whenever you see it, you should reverse the index but keep the dyad sequence. Transpose, you should keep the index but reverse the dyad sequence. Remember this. So we have C, which is a quadratic tensor. We were there. Okay, C is a quadratic tensor. It's like F transpose dot F. It's sort of like F squared in a very loose sense. So C can be spectrally decomposed as C is equal to alpha equals 1 to 3, lambda alpha C, gamma alpha, gamma alpha, gamma alpha C, gamma alpha C. That is, you are given F, you compute C. From C, you can get its eigenvalues and eigenvectors. Okay. So this is the spectral representation of C. Okay. And why would we care about spectral representation? Because when you write C in this fashion, that is, if you use the eigenvectors of C as its basis, you basically write this is equal to lambda alpha C or lambda 1C, lambda 2C, lambda 3C, 0, 0, 0. You are expressing everything in terms of a stretch. Only the diagonal terms matter. The off diagonal terms don't matter when you represent it in spectral form. How would you translate that to a physical situation? When you have a loading, an arbitrary deformation which is expressed as F, and then you reduce it to an eigenform, what is the equivalent of that in real world? Here is two-word hint. If you've taken basic courses in undergrad, what does the Mohr circle represent? What when you use the Mohr circle to calculate a bunch of directions, what are those directions or what is their significance? Okay, in the interest of time, I'm going to speed things along. These directions represent the eigendirections in which the deformation is purely either a tension or a compression. You are essentially identifying directions where you don't have any shear. Okay, that is what this means when off diagonal terms are seen. So what you need to know is, first we need to be able to calculate J or J, and using F we are calculating C. We are expressing its spectral form. Similar to C, you can also think of what is B. B is F dot F transpose. Again, question for you, is B a spatial or material tensor? You can go through the same thing again. F is Fij, Ei, dot F transpose is F. I'll call it JK EJ. Sorry, transpose would be reversal, right? EK Ej. So I will have Fij, Fjk, Ei, Ej, and then delta Jk material. So this is Fij, Fjj, Ei, Ej, which is a second order material tensor. You can again go through the same procedure and express B is alpha equals 1 to 3, lambda alpha B, gamma alpha B, gamma alpha B. This would be a material vector. This would be a spatial vector. Okay. I brought this up because we introduced C. I might as well introduce B. Okay. We talked about volume change. That is section 3.4.2. So I'll start making a list here. 3.4.1. What was that? Deformation gradient F. 3.4.2. J equals dV over dV naught. Or I'll write J times dV naught equals to dV. 3.4.3, we talked about area changes, which is the relation I previously wrote. N cap times dA is J F inverse transpose dot N cap dA naught. I mean, what I'm trying to say is you should be able to use these relations. The problem will read like this. You'll be given a deformation. That is starting point. So typical problem would give you x equal to phi of x. Typical problem in section 3.4. You'll be given this, compute any of these combinations f, j, dx, dA naught, or n cap times dA naught, dV naught. Either compute this or the equivalent spatial quantities dA n cap dV. Okay, so this is the typical. And then, of course, I keep adding to this. Yeah, I'll keep that. Then we have 3.4.4 polar decomposition here. So that is like writing F is equal to R dot U, that is equal to V dot R. Anybody recall the interpretation we gave for this, writing F as the product of a rotation matrix and a stretch matrix? Either it's a rotation followed by a stretch or a stretch followed by rotation. The only difference is U is the square root of C. So this would be alpha equals 1 to 3 lambda alpha C square root gamma alpha of C. So if C is a material tensor, U is also a material tensor. So it's like saying any deformation is a pure rotation, sorry, it's a pure rotation in mixed coordinates followed by a stretch in the material coordinate. Or it's a stretch in the spatial coordinate followed by a rotation, pure rotation. B is square root of B, which is alpha equals 1 to 3 lambda alpha B square root gamma alpha B. So this is a spatial tensor. So it will also ask you to decompose or calculate R, U, B. So I did do the next section, which is actually this is not 3.4.4, this is 3.4.5, and 3.4.4 is push forward and pull back operations, which is more like a concept. So there may not be a direct problem, but you will apply that idea. Okay. We also did 3.4.6, but not really to my satisfaction. So we'll skip that for the exam. You don't have to study it for the exam. As far as 3.4 goes, 1, 2, 3, 4, 5. That's it. Okay. 1, 2, 3, 4, 5. That's it. So to complete this roundup, we are going to get one problem from this section, one problem from this section. That's two problems. And then section 3.2 and 3.3 combined, we will have one problem. And then section 3.1 will be the subject of a conceptual question. So that's your four problems, which is 3 plus 1. Okay, so that wraps up this whole topic. We'll take a break. 607 will assemble at 613 and we'll do some examples. Okay, thank you. Can I erase it? Have you taken a picture? So welcome back. I already told you that we are going to have three numerical problems, each based on one of the sections. So I'm just going to start by looking at section 3.6 and suggesting from the book which are all the type of problems which will fit under this template, so that you'll have some reference to practice. And maybe we'll pick one problem and try to solve it. And if you did the homework, most of it is something that's covered in the homework through the problems. That's the intention of the homework, to get you to practice on this. Okay. So we hope we have written this down so I can erase this quickly. All right. So problem or section 3.6. What are the type of problems in the book? 3.19. Anything that has time dependence, basically 18, 16, 15. So these four problems are the ones that include time dependence. And if you think of section 3.4, that would be problem 3.14. Actually, pretty much from 3.1 to 14. All of them involve both section 3.4, all the measures that we described or saw in 3.4. Of course, it also involves the basic concept of what is deformation, x equal to phi of x, and from there getting the deformation gradient. That is basically section 3.2 and 3.3. So it's sort of included in all of that. So I can pick out examples. I would rather have you ask something which we can discuss. Anything that in the homework that you felt like you want to discuss, we can talk. Most of it is, if you look at, for example, I'm going to read a couple of problems here. Section 3.7, sorry, problem 3.7. Problem 3.7, they give you a deformation, that is x equal to phi of x is given. And then they ask you to calculate f. They ask you to calculate the decomposition f is equal to r dot u. And then they ask you to calculate, consider a line element dx lying along x1 with length ds. So dx, how will you write dx? It is lying along line at direction 1 with a length of ds. So how will you write it in vector form?
Sorry.
So dx is a line element of length ds lying along the direction 1. So how will you express that as a vector? So if you want me to draw a picture, here is direction 1. Here is ds, a length element that is oriented along the first direction. And then there is direction 2 and 3. So vectorially, how will you express this element? This is vector algebra, so it should not be that complicated. Right? It's like writing ds equal to or dx equal to ds E1 cap plus 0 E2 cap plus 0 E3 cap. Okay. The question starts here. It says, consider a line element dx lying along x1 axis with length ds. Under this deformation, the line element is stretched and rotated into a line element dx, made d spatial x. Okay. Calculate the length ds lowercase, which is the magnitude of dx. You subject this element to this deformation, it will undergo a change in shape, change in length. They are asking you to calculate the length change in the spatial form. You did this homework, I think. So what did you do? Okay, step one is you need deformation tensor. You can do that, right? I assume that is you can go through this derivation process and write Fij is partial xi over partial xj. You can do this. Good. If you want to get dx, what is the fundamental relation? Dx is f dot dx, which is Fij times dxj, right? Whatever Fij is, which we can calculate separately, we know dxj has only one non-zero element. Only j equals to 1 matters. J equals 2 and 3 don't matter because dxj, dx2, dx3 are 0. So this is fi1 dx1 and dx1 has a value ds. So I'll write this is dx1 or fi1 ds. That is dxi equal to fi1 ds. fi1 ds. dxi. With me so far? Okay. So then I'll write dxi is fi1 ds. What is ds? What is ds in the spatial frame? That is dxi square root. Right? dxi square root. Okay. So this here, it's like writing dx vector is f dot e1 ds. I mean, you don't have to do this, but what I'm trying to say is, if this is dxi dx dot would be fi1 ds which will make this fi1 squared ds squared. So this is going to be fi1 ds. This simplification is possible only because we have a very special case where dx is oriented along a particular axis. If ds were drawn at some random angle, like if dx is written as, we'll write dx equal to ds1 comma ds2 comma ds3, then this simplification won't be possible. Okay, so if I want ds, I need to do this as fi1 square root. So that this index summation is taken. But the overall flow is first to get the f. If you know the f as a function, you can knock off everything else. So every problem invariably will start with this, whether you like it or not. Okay. Can you please go ahead, complete this problem? I'll give you like 5 minutes. Start with this x, compute the deformation tensor. Let's verify we are both getting the same, all of us are getting the same thing. And then we can move to the next problem. So look at problem 3.7. If you want, you don't have your book with you, I can write it out. So I'm going to write x1, x2, x3 equal to deformation tensor -1, -2, -1
Under root 2.
square root of 2,
Minus 2
2 root 2, 0,
1 2
1, 2, 1 multiplied by x1, x2, x3. So if you write it in matrix form and your deformation is a linear function with respect to x, that matrix is just your deformation tensor because it's linear. So if this is your f, this is your f. You want dxi or dx is f dot dx, which is like writing fij dxj ei cap. And we do know that this is equal to fi1 dx1 ei cap or fi1 ds ei cap. So first question, what is the change in length, which is the magnitude of dx, which is dx dot dx square root. What is dx dot dx? That is like writing. So remember this is dx. Dx is dxi ei cap. So if I want dx dot dx, that is dxi dxi, which is fi1 ds squared. So if I want this as the square root, this would be square root of fi1 times ds. fi1 is not just the product of two terms. It's the summation over I varied from 1 to 3. You know that, you know this, I'm just recapping. This is shorthand for I equals 1 to 3 fi1 times ds. Now look at your matrix f11, f21, f31. 1 minus 1 squared plus square root of 2 the whole square plus 1 squared. 1 plus 2 plus 1 is 4. Square root of 4 is 2. So this is 2 times ds. None of the problems will be like mathematically, arithmetically super challenging. It will be all these very simple operations. Okay. So that was part 3A. This is part 3A. Okay, 3A. That is under problem 3.7. This is part 3A. Calculate, I'm reading part B. Calculate the vector dy, which is u dx. So here. So calculate dy in the spatial frame, which is u dot dx. And they also say, show that and show that dy, which is the magnitude of the vector dy, is equal to ds, which represents all the stretch is in dy itself. We'll come to that in the end, but first let's get u. How do you get u?
C.
U is, for getting u, you need C, or you need, if you want u, you need C. And what is C? C is F transpose dot F. So if you know your F, it's a question of matrix multiplication. You need to do what is F transpose dot F. So this is F. I'll write the transpose minus 1, minus 2, minus 1, minus 2, minus 1. This is square root of 2, 1, minus 2 root 2, 2, 0, 1. This is the transpose. This is transpose. And then you have to multiply the transpose with the matrix itself, minus 1, minus 2, minus 1.
Yes.
This is, which is plus 1?
Minus 2, minus 1, plus.
This is plus 1?
Yeah.
Yeah, that is plus 1. So you have minus 2, minus 1, 1. Square root of 2, minus 2 root 2, 0, 1, 2, 1. See, for linear transformations or linear mapping, it boils down to just vector algebra. Sorry, matrix algebra. You have to take the transpose, multiply with the matrix itself, you will get another square matrix, which is C. But when you use matrices to represent your tensors, what is not specified in the matrix notation is which frame of reference are you referring to. You can write a matrix. F transpose dot F is just multiplying two matrices, but the result of it is C. It doesn't say what frame of reference. It doesn't say material or spatial, but you have to remember that. Okay, so you can get C, which is the product of these two, and then you have to get the eigenvalues of C, which I'm sure you did for your homework, right? So when you did the homework, you would have a sense of how long will it take to get the eigenvalue of a 3 by 3 matrix. For some it might take 2 minutes, for some it may take 15 minutes. So you have to time yourself in the exam. So the exam is really going to boil down to how much have you practiced? Okay, whether can you do this in 80 minutes? It's not a question of whether you can do it at all. You can do it. All of you can do it. In 80 minutes, can you do it? Okay, so practice. So if you have u, you can do u dx. Okay, you tell me this. U dot dx, will that be a spatial or a material vector? Did you say material? See, I already wrote this is dy. So I already gave a hint that this is spatial. And if I don't give you that hint, you still should be able to think what is C? C is a spatial or material? C is material, right? C is material. So U should be also material, right? So U dot dx, something is wrong here. Hey, that sounds to me like a typo. Because listen to this. Calculate the vector dy, which is given as u dx. That's what the book writes. And show that dy is equal to ds. This shows all the stretching is represented by u. I would think this is uij dot dxj, which would make it a material vector, which I agree with you actually. But the book for some reason calls this a spatial vector, dy I. That doesn't even make sense. So I don't know. If I were you, I would say this is a material. Unless we do the other quantity, where if you had Vij multiplied by dxj, that would be a spatial vector. Okay. So at a graduate level, you're not expected to always agree unconditionally. Even at the undergraduate level, there should be disagreement, there should be questions. So just because it's in the book, I don't want you to accept it. I'm seeing this for the first time. Maybe if I'd seen this earlier, I would have said something. But we have taught you the principle. The principle is you do a dot product. This is material, you would end up with the material. Let's stick to our principles. Okay. Good with that? So the part D of this problem, calculate the vector dz. Calculate the vector dz, which is r dot dx. R is okay. You remember the polar decomposition? F is equal to Ru or R dot U. F is mixed. U is material. So this is like writing Fij is, I'll write it Uij. This has to be Rij. Sorry, Rii. So if I take R, which is a mixed second order tensor, and if I calculate R II times dxi, I will get dzi. So here we agree with the book. If we follow the same logic, here we end up with the spatial vector dz. But I still believe this must be dy. We can write a email to Dr. Tadmore, who I still know, and say, I can ask him. I mean, he's still our teacher, metaphorically. He's my teacher, so he's also your. Okay. So I believe this has to be a material. So at the basic level, it comes to really index notation and understanding basis vectors, dyads, dot product. That's all it comes down to. No more complicated than that. Any questions? So while you are doing the homework, is there any particular problem that you wanted to try in the class or ask? Yes?
Some of the questions they asked us to write down,
Yeah.
which we will have with.
Okay. So it's like you can expect this kind of a question. You are given a deformation through a function, and in the laboratory, you start with a sample. Usually you make the sample to be a known shape, and you call that shape as your reference configuration. And a shape like a cube is very unit cube is very convenient because it allows you to think. It at least gives you some limiting cases. So if you have a unit cube and you stretch it along direction 1, you know the length is going to increase along that direction and also going to decrease simultaneously along direction 2 and 3 because Poisson's ratio will allow for volume conservation. Or if you do a shearing operation, or if you do an oblique, some kind of loading, the question always is, if you start with a unit cube and call it or use it as the reference configuration, and you subject that cube to a deformation, draw the final shape of the cube after deformation. Okay? How do you think about it? What is a deformation? Think closely. You have a bunch of points which you call as a reference. What does a deformation really do according to this equation? Not only orientation. Yes, it does shift orientation, but also shift position in the sense. If you just say shift orientation, it's like saying, I'm looking at you. If I move this way with respect to your direction, my orientation has changed. So I have not only changed my orientation, but also my position. Usually it involves both. So you have your unit cube. A deformation is literally your unit cube. Every point on the cube denotes a material vector. Right? That's what the reference configuration. This mathematical equation literally states every point is mapped onto a new point. That's why we call it mapping. Literally, you have a cube bunch of points. Every point maps onto a different point. And if it's an incompressible material, you can't compress all of them to the same point. They have to have all their each separate point because volume is conserved. So if you are having a unit cube and you are kind of, let's say it's a bunch of clay, okay, mud and water. You can do any kind of shaping, it will change shape, but the volume will still be the same. It's a volume preserving deformation. Let's say it's a small cube of metal that you are putting in an angle and just compressing it to a point that you are actually increasing the compressive strain, which is basically like saying the final volume is slightly lower than the initial volume. That is not a volume preserving deformation. Okay, so every point in that reference cube cannot have its own new point in the compressive deformation because compression literally means volume has shrunk. So some points have to now share a space or some atoms have to move closer together so that they will occupy lesser volume than before. Okay, so your question is, if I am given a cube according to this deformation, how would I map the shape onto the spatial configuration? That is your question. Any thoughts? Anybody wants to say like how would they answer this? Any thoughts about this? Yeah.
You can just select, if it is cube, you can select, 6 corners.
And map where those corners will first land. So you can take 6 points, you can plug them in, and you will get 6 points in the spatial frame. If all 6 points are still the same, it probably means there is not much shape change. But if suppose you are lengthening it or stretching it in one direction, if you are initially like this, at least you will become like this, or you'll become like this, or you'll become like this. So that will give you some idea about the 6 corners. But if you have a length element, it is oriented along direction 1. The question is, in the final configuration, you have 2 points. Suppose you have the same 2 points, the length hasn't changed, but the orientation could have changed. They could have rotated. Maybe it was not just a compression, maybe it was torsion. So you got twisted. Your length is still the same, but your orientation is no longer along axis 1. It might be at 45 degrees or whatever degrees. So you need to take, starting with points. Where do the 6 points map? Then go for 6 lines, or not 6 lines. How many edges does the cube have? Quickly tell me. That's 6 faces. What about edges?
8.
8 edges. So you can start with maybe the simplest, which is along the direction 1, and see whether it is mapped onto the same direction. So direction 1, so x-axis, y-axis, z-axis, have they changed orientation? And then there are 4, you have 4 more edges, of course, 1 more edge. So you can go first points, then edges, then area. So face 1, which is along x-axis and y-axis, that face still the same. You can map an area vector onto a new area vector. So if you do these calculations step by step, you will start getting intuition about what the final shape will look like. So it literally comes down to this. Four-step calculation. Okay. You don't have to do this as a calculation. The calculation is supposed to help your intuition. So step 1, points, x equal to phi of x. Step 2, line elements, dx equal to f dot dx. How do you define a line in a vectorial form? That is, if you have 2 points, let's say this is point 1, this is point 2, this is x1, this is x2. You can define a vector, call it L, and it might be x2 minus x1. I'm not saying you should always orient your cube at the origin or anything. You can be anywhere, but you can define this direction as L x2 minus x1. Once you calculate this, it's just a bunch of 3 numbers, right? So you can say what happens to L, which is f dot L. So if your original line element is along a particular direction, you can predict what will happen to that line element due to the deformation. So it's like asking, I have my unit cube. Let's say one of the corners of the cube is 0, 0, 0. What will be the coordinate of the diagonally opposite corner? Is it square root of 2, square root of 2, square root of 2? No. So this is for simplicity, I'll do it in 2 dimensions, 0, 0, 1, 0. So this is 1, 1. I have a line which is represented as L equals 1, comma 1. If I subject that to a deformation, I'm asking what is the new orientation of my diagonal, which will be F dot L. So in your mind, either you can do this all in your mind and just draw the final shape, or you can calculate each orientation or each change separately and use that information to construct a diagram of the final shape. That makes sense to you? I don't have like a 2-minute answer to you, but it's the process. And the question might break it down for you. It might ask questions like, for this deformation, what happens to a line element that is oriented along a particular direction? What will it be its orientation in post deformation, or an area element which is initially oriented? So yeah, I was talking about this, right? Line elements either change in length or the projection in the new coordinate system. You can apply the same principle for area elements. N cap dA equals J F inverse transpose dot N cap dA naught. So the interpretation of this statement is the initial area defined by the line along the x-axis and the line along the y-axis, the face that is perpendicular to axis 3 has an area of some units. Okay, what is n cap? N cap would be E3. You subject it to a deformation, all that information is captured under F inverse transpose and J, which will take care of the orientation change. And then you will get n cap. So it goes both ways. If you think physically, you can predict the math, or if you practice the math, eventually you will start correlating the math to a physical behavior. We are in that second stage where we want to do the math first and use that to guide our intuition. And the more you do it, it'll start appearing the other way. If you have thought of this enough number of times, you can look at a deformation and say, oh, this first phase is going to do this orientation change, or get square is going to become a rhombus of 45 degrees or whatever. And this is one of the main tools people use in crystallography, where they have crystal structures. They use deformation. So you have a FCC or BCC, and you subject that to a loading. They then predict what happens to the structure post the loading, because you initially had certain symmetries which are stored under this element orientation. And it carries also over to volume elements, where you can write dV equal to J times dV naught. So what's the final volume? What's the initial volume? And so on and so forth. So you should use a combination of points, lines, areas, and volumes to answer that question. And you should use all this to finally draw a diagram of what happens to a cube. It will be a cube. I'll always ask only cube. Given a unit cube in the reference configuration, what is the final shape of that cube in the spatial frame? That's the question. I actually thought I'll give like a mock exam, but we are kind of entering the last 20 minutes, actually 25 minutes. So here's what I'm going to do. I'll send a mock exam by tomorrow, but today we'll just continue doing exams until 7:25. Any other problem that you wanted us to discuss?
$8.8. Okay.
3.8 to 8. Okay, you are given a deformation example of a pure stretch deformation, okay, and compute that is under part 2, compute the components of the deformation gradient and the Jacobian J of the deformation, which is easy. What conditions do the parameters P and Q need to satisfy in order for the following conditions to be met, each separately? That the deformation is invertible. Give an example of a situation where this is not satisfied. Draw the result in the deformed configuration and describe the problem that occurs. What do you mean invertible? That is the question. You are given a transformation x equal to phi of x. What does invertible mean mathematically? Think of it as a function. Input, output. If you can give an input to phi, you can get x. If you can specify x and get a unique material x for that, that would be an invertible function. Right? The inverse exists and is unique. A given value of x map exactly to one point in the spatial coordinate, and every point in spatial coordinate maps uniquely to a point in material coordinate. That would be an example of a invertible function. So the question asks you, for what conditions do P and Q need to satisfy for the deformation to be invertible? This is a basic matrix algebra question if you think about it. What is invertible? So you first step is you look at the deformation. X1, X1, X2, X3 is equal to a matrix which is 1 plus P Q0, 1 plus P Q0, Q 1 plus P 0, 0, 0, 1. X1, X2, X3. So physically invertible means for every point in the material frame, there exists a unique point in the spatial and vice versa. Mathematically, this is the relation between spatial and material. If you want to say, you want to write the opposite and write F, or if you want to write this is x equal to F dot x. You can write this is x equal to F inverse dot x. The simple condition is F inverse must exist, or in other words, this matrix must be invertible. Inverse of this matrix must exist. And what is the condition for that? For you go to matrix algebra class or your mathematics class, when they teach you inverse of a matrix, what's the first condition to? Determinant. Determinant should not be 0. In our language, J must not be 0. J must not be 0. You can work out J, which is 1 plus P whole squared minus Q squared, and you don't want this to be 0. So if you expand this, if you expand this, 1 plus P or Q should not be equal to plus minus 1 plus P. If this condition is satisfied, then this thing is invertible. So it's not a question of testing your mathematical abilities. It's a question of making sure you understand what these terminology mean. If you didn't know what is invertible, you are done. You can't do this problem. Not that you cannot calculate matrix or anything. You know that. Okay. Give an example of a situation where this condition is not satisfied. Draw the result in the deformed configuration and describe the problem that occurs. So this situation happens when your Q is equal to 1 plus P or minus of 1 plus P. So just choose Q equal to 1 plus P. Let's see what happens. Q is 1 plus P. This whole thing is like writing 1 plus P, 1 plus P. You can't invert it. No point in trying. Okay. What is the implication of this transformation? That is, you will write x1 is 1 plus P times x1 plus x2. X2 is also the same thing. X3 is x3. If you choose Q is equal to minus of 1 plus P, you will get 0, 0, x3. Zero, zero, x3. What is this situation and what's the problem with it? Okay, if we are not able to answer that right away, draw the result in the deformed configuration and describe the problem that occurs. Start with your approach. First map the points, then map the lines, then the areas, then the volume. Volume is 0. The J is 0. Wait, sorry. Yeah, J is 0. Correct. J is 0. So what happens to the points? So if you take, I'm going to say material or reference configuration and spatial configuration. What happens to 0, 0, 0? Space 0, 0, 0. What happens to 1, 0, 0? 1, 0, 0 becomes 1 plus P, 1, 0, 1 plus P, 1, 0, and 0. So this becomes 1 plus P, or I'll say 1 plus P multiplied by 0, 0, 0. Sorry, 1, 1, 0. So this is like saying an element which was originally along the x-axis is now oriented between 0, 0, 0 and 1, 1, 0 scaled by 1 plus P. And for now, at least we'll assume P is not equal to minus 1. What happens to 0, 1, 0? What happens to that point, which is here, 0, 1, 0? Where does that get mapped onto? It also gets mapped onto this same point. Would you agree? This gets mapped onto here. This also gets mapped onto here. Do you agree with that? How am I saying that this gets also mapped onto here? So I'm going to use two colors to distinguish between spatial and material. Okay. So let's use the green to draw the material or the reference configuration. So we have direction 1, direction 2. Here is 0, 0, 0. Here is 1, 0, 0. Okay. Now if I plug in 0, 0, 0 into here, into this, I'm going to get again 0, 0, 0. So this point, its mapping is 0, 0, 0. What happens to 0? Sorry, 1, 0, 0? That gets mapped onto 1 plus p times 1, 1, 0. So we'll say here is 1, 1. 1 comma 1 comma 0, and we are multiplying it by a factor 1 plus p, and we'll assume p is not equal to minus 1. So depending on what its value, it could be over here, it could be anywhere on this line. Could be anywhere on this line. Would you agree? Depending on what the value of p is. For simplicity, if we even say p is equal to 0, which is okay, then at least at the minimum, this line, it is getting stretched along this diagonal. With me so far? Consider this point, 0, 1, 0. According to this equation, this mapping, 0, 1, 0 also gets mapped onto the very same point. Agreed? So it's like saying two faces have collapsed onto the same point, or say two faces have collapsed onto the same, two edges have collapsed onto the same line. Okay? What about 0, 0, 1? 0, 0, 1 maps to 0, 0, 1. So any point that is not on this plane or any point along this line is not going to change at all, and that's what this third line means. But if that is the case, these two lines have collapsed onto this diagonal, and let's work out one more point. Let's think there would have been a point 111 or 110, right? What happened to that point? If I plug in 110, there is p is 0, so forget it. It becomes 220. So 220 would come somewhere here. What kind of weird shape is evolving here?
Three-dimensional object compressed into
Basically, you are going to get a sheet. You are going to get a sheet that stretches from outside the plane. That is the equivalent of doing, like you take a block and a hammer and you hammer it until you get a sheet. Well, you know, if you do any sheet metal work, it's not that the material you have is zero thickness. Even if it is atomic thickness, it's still thickness. So mathematically, you are collapsing it down to a line, like a volume into a line, which is not possible. So the problem that is emerging here, that is, describe the problem that occurs. The problem is that a finite volume has now been flattened into a sheet with zero thickness, and there is no account of where the material went. You know, in reality, material can't vanish, but mathematically it does. So that is the problem. Okay. All right, any next problem? We have about 10 minutes. Actually, we have 15 minutes. Shall we do something related to section 3.6? First thing I want to do is problem 3.16. Problem 3.16, part 4. You are given x, that is, you are given problem 3.16. You are given x equal to phi of x comma t. This is the motion where there is a dependence on both x and material x and time. What is asked is calculate the inverse motion x equal to p inverse of x comma t. Did you do this during your homework? So can anybody tell me like a strategy? So it's easy to say I'll have phi and then do phi inverse, but in reality, how do you do that? Say it again. No, first you need to look at, I mean, this is vectorial representation, right? In the problem, they have given what is x1, x2, x3 as a function of material x and time. They have given it literally, which you have to use. So this requires some algebra. So I have x1 is x1 squared plus x2 squared divided by 2b times 1 plus time, and then x3 is c times tangent inverse of x2 over x1, and then sorry, this is x2, and then x3 is b over c times 1 plus t times x3. You can keep time, but you have to eliminate or express x1 in terms of x1, x2, x3 and time. So this requires literally some algebra skills. Sometimes it'll be easy, sometimes not so easy. Okay. So what do we do? Where do we start? So this looks the simplest to me. X3 is the simplest, right? So we can write x3 x3 is c over b times x3 divided by 1 plus t. That looks simplest. These two equations involve only x1 and x2, so that is good. That is good. So we can take the second equation and write x2 equals x1 times tangent of x2 divided by c. Okay. So then this becomes x1 squared times 1 plus tangent squared of x2 over c divided by 2b times 1 plus t. It doesn't look pretty. I'll give you that. This is 1 plus tangent squared, which I remember is secant squared, right? Secant squared. So this gives us x1 squared is equal to 2b x1 1 plus time, and then you have secant squared, which with this side it becomes cosine squared of x2 over c. So x1 is, we'll take the positive square root, 2b x1 1 plus t square root cosine of x2 over c. So there is your x1, and then x2 you can write. What is x2? What is cosine multiplied by tangent? That will be sine. So this will be 2b x1 1 plus t sine of x2 over c. And x3 is t over b x3 divided by 1 plus t. This is the inverse motion. So just a couple of bunch of algebra steps. Okay. This is not the interesting part. The interesting part comes after this. Part 5. Find the velocity field in both the referential and spatial descriptions. How will you find velocity or material velocity? This, I gave you a quick step guide when we did this. So material velocity V with a tilde of x comma t is given as partial x over partial time for a fixed particle. So you would take this expression, differentiate this with respect to time while treating material x1, x2, x3 as constant. So in that case, V1 tilde, V2 tilde, V3 tilde is equal to partial x1 over time, which is equal to minus of x1 squared plus x2 squared divided by 2b times 1 plus time whole squared. And then this has no time dependence, 0. Partial x3 over partial time is p over c times x3. That's it. This is the velocity field in referential description. From here, how would you push forward to the spatial description? Double what? Use this function. Use this function to replace x1, x2, x3 in terms of spatial and time. Done. So substitute for x1, x2, x3 in terms of that. You're done. This is velocity field in referential, and then you can use x equals the inverse motion phi of x comma t to get velocity field in terms of x and t. Good. Everybody is going to knock this out of the park on Tuesday. Good. Good. So this is velocity, right? What about acceleration? Acceleration is again computed as acceleration in the material frame. X comma t is the second derivative of position with respect to time at a constant particle. Differentiate this further. So you are going to get x1 squared plus x2 squared times b over 1 plus t whole cube. And 0 and 0. And then again, use the inverse motion x equal to phi inverse of x comma t to get acceleration in the spatial field. Last 5 minutes. So I want to do one application of that Reynolds transport theorem. Okay. Is clear? So part 6 talks about a scalar invariant field or scalar field given as G bar is G tilde of x comma t, which is given as A, which is a constant, times x1 times x2. This is G. Find the spatial description G of x comma t. So what you would do is again use x equal to phi inverse of x comma t. Basically substitute for x1 and x2 and get in terms of spatial x. Same operation you did for velocity and acceleration. Just another quantity which is defined as x1, x2. Okay. Find the material derivative of G in both material and spatial forms or Lagrangian and Eulerian representations. So we want to get dg tilde over dt, which is g tilde over t plus gradient of g tilde with respect to xj times vj, which you can also write g tilde plus g times divergence of p. This is Reynolds transport theorem, by the way. Just want to make sure I got everything right. Sorry, this will be G dot. So if you have G, you can differentiate that with respect to time. If you have V, if you have this V, you can compute the divergence of this V. You can combine those to get the material derivative. Okay, so I erased what I wrote there. Literally, you would substitute for x1 in terms of x and t and x2 in terms of x and t to get a G. And then all you have to do is this G dot is nothing but dg over dt while holding x constant, and G is given here, and this del dot V is partial Vi over partial Xi. So this is the material derivative in Eulerian or spatial representation. Eulerian or spatial representation. If you use x equal to phi of x comma t, you get the Lagrangian or material representation. That concludes the problem. It's always a question of calculating in something that is convenient and then keep using either the motion or the inverse of the motion to go back and forth, push back, pull forward, push back, push forward, pull, so push forward and pull. Okay, so this is a good place to stop. So on